So it was pretty rough waking up this morning. It was very hard to roll out of bed, and I don't know. We need to dig deeper to keep this going for like, what, 6, 7 more weeks? Probably the whole semester, if not the whole year. So today's lecture is on focusing on Unit 3. Math.random came from Unit 2. Unit 3 talks about Booleans, logic, and if statements. So as you're working through the CS Awesome assignments, be sure you're making use of this blue text down here where it says question in context. If you're stuck on a particular coding problem, click on that and it brings you to the web page or part of the course, part of the interactive textbook where it has some useful videos and or diagrams and paragraphs explaining ideas related to that problem. Also, let me skip some slides and go back a bit because I get multiple emails about this. Just so that you are not doing extra work, right? Be sure you're going here, clicking on your face, going to assignments, and clicking on Unit 3 to be brought to this page, and then scrolling down to work on those problems, because you'll notice, like, I don't think I assigned the turtle dancing. I might have, but I unclicked and unchecked some of those challenge problems, for example, and I only assigned like the stuff I care about, like lots of if statement practice, that kind of multiple choice. So if you feel like you're spending a lot of time on the CS Awesome, be sure you're just doing the problems I assigned. You may be doing extra work. Okay, back to here. Okay, so Booleans, those are one of the data types in Java. Do you have to do every problems within the readings? The one reading section with math.random, I think it wants like 8 or so out of 12 interactions. So not all of them, but if you want to secure that like green bar at the bottom, be sure it like passes over, like there's a magic number there, and I think you see it on the assignment page, and I think it's 8. If you do that, you'll get the point. All right, Boolean variables. They're the simplest and smallest primitive data type. They can only store true and false, otherwise known as zeros and ones, 1 being true, 0 being false, 1 or true being yes, false being no. If you think about the circuit tree, true is there is power going through the circuit, and false, it's like the light's off, there's nothing going through. Where's my pointer? Here it is. So then down here, going back to that data type idea, we have noticed that true and false, right? They change colors in whatever ID you're using. They change color in CS Awesome. So in this one, notice false is all lowercase. True is also all lowercase. Some languages may choose to capitalize the F and the T, but in Java it is all lowercase. And those, this is how it works, right? Storing it, initializing and declaring it, to review some vocabulary. And then in line 7 down here, notice we're trying to put an integer, 30, into a Boolean, how big, and then it tells us, oh, you can't do that, type mismatch. Just like with the 4-4 assignment, when you did 3 plus 3 versus quotation mark 3 plus 3, closing quotation mark, those two things are different. True without quotation marks and false are reserved, those are Booleans. But then true and false with the quotation marks, those are strings, words and sentences. We'll talk more about this string object second semester. But if you want this exact thing to print versus the value, although when you run the computer, right, like you press the play button, the output looks the same. Go say like TRUE, and then the other one will also say TRUE. The computer sees them as different things if you initialize them to be like true versus having the quotation marks here and here. Okay. So the other new idea, logical operators. We have ands, ors, and not. Okay, the 2 ampersands, so that's shift 7 on most keyboards. 2 of them, no spaces in between, that means and. These things are parallel bars. To input those are typically above your a return key, shift, and you press like the backward slash. There's no space in between them, it's two parallel bars. And the exclamation mark in Java is known as not. These are logical operators, sometimes called Boolean operators. And just like with 4-4s, right, these things manipulate some values. Specifically, they manipulate like Boolean expressions instead of like numbers, right, in the 4-4s assignment. So you use these, combine them with like trues and falses or expressions that mean true and falses, and get like one overall true or false statement. So I think it's easier to go over examples of these, like what do ands, ors, and nots mean? Think back to geometry and truth tables. Okay, we'll need it. So over here, ands, oh gosh, my pointer's acting funny. There it is. Okay, so here, the table, okay, you see my mouse, yeah? My pointer like keeps disappearing. So over here with the ands, the first input here is true, and true gives you true. False and true gives you an overall, overall expression of false. False and true gives you false, and false gives you an overall statement evaluation of false. So that's how we read them. So then can you answer these three in your head? Good. False or true, that would match either one of, let's see, false and true, this one here, or this one here, either of these diagonals. Overall, it is true. True and false. That's how I'd read that in plain English. True and false, that would be false overall. This one's a little weird one. It just read not true. So what's not true? Otherwise known as false. Okay. We'll get more practice with combining all these things. Things you're more used to, I think, especially from math class, are these symbols known as relational or comparison operators. The first 4, I think you know. This is the greater than or equal to sign. This is the less than or equal to sign. And then these two may be a bit new. Not equals, right? Exclamation mark equal sign is the not equal operator. Double equal signs is checking, right? Is it equal to? These 4 work the way you want. If the two things don't match, then it is true. If the two things do match, then the overall expression is true. So apply some of these ideas. What would be the output? What would be printed to the screen? And you can type into chat. Should it be true? Should it be false? Is there an error? And we'll go through 3 or so of these examples. No? Nothing? Cool, thanks. Cool. So we're getting there. We're awake. So if you wanted to show your work through how to work through these, you would substitute in 150 here. The recording's not going to pick up on these zoom annotations, but at least you all can see them as I'm writing them, right? First do a substitution. Evaluate this expression here. So that's going to be true. Bring down the and. Then is 150 less than or equal to 100? Nope, it's false. Now this part is much easier to work with. What's false and true? Since you see it has a false in it, you know the overall expression has to be false. Okay, if you want to take a picture of that, go ahead. We're going to go on to the next problem. you're right. Put it in the code, it gives us false. Here's the next one. Notice the value got changed a bit. What is the overall expression? I'll put a break right here. And just like before, type in the chat. What would be printed to the screen? Very good. We're getting a bunch of trues. Yep, it is true. 50 is in fact bigger than 0, and 50 is less than 100. So overall, the expression reads true. Nice. Let's practice some other operators. There's a couple of changes that happened here. What would this be evaluated to? We've changed the first line where we initialized it to a different value, and now we change the operator. How would this work? Very good. 150 is bigger than 0, or 150, is it less than 100? Nope. But with ORs, you just need one of them to be true. So already we met the condition on the left-hand side. Yep, good job. So the not operator is a little weird. The ands and ors both took two things on the left-hand side and the right-hand side. They took two expressions. They took two Booleans. So nots only need one. Okay, and what it does is it flips the value. So if here the Boolean is what is initialized to be true, it's also declared with this keyword, and then you print exclamation mark is what, this flips the value of is what. So thus you see false being printed to the screen. Think about not as the opposite operator. That helps you. And here's illustrating that flipping idea some more, right? This line 6 and line 8 is very common in computer science, to flip the values of whatever you're working with, the Booleans that is. So notice it's is what in line 5 starts as true. You flip it. Is what equals the opposite of is what. Reading it as is what equals not is what. It's a little funny. So opposite tends to work better here. When you print the value to the screen, you see that once was true is now false. Flip it once again in line 8, and then output it. Line 9 gives you true. Short circuit evaluation. So we know things about ands and ors, and the computer just makes use of that knowledge to make itself a bit more efficient, right? So notice with ORs, as long as you see one true, right, and because the computer reads code from left to right, when it sees true on the left-hand side, it doesn't matter really what's on the right-hand side of these two parallel bars, right, the OR operator. It already knows the overall expression is true. And similarly, for ands, if you see on the left-hand side, you see a false, doesn't matter what comes afterwards, the overall expression is always going to be false. So when you can ignore like the right-hand side or whatever comes after your operator, that's called short circuit evaluation. So let's make use of that. What is the output of this expression? What does it evaluate to? And then, sorry, let's put that in chat. Okay, you got it right. So I have a visual break and checking. Awesome. So for those students like thinking about it, it should be true. You should get it kind of quickly because you ask yourself, is -3 less than 0? Yes, or true. You can ignore all this stuff on the right-hand side. Don't even look at that because you are making use of short circuit evaluation. You have an OR, you see a true, so overall it has to be true. And that's exactly what the computer does. Okay. How about this one? what does this expression evaluate to? Oh, yeah, Garrett's the last one. Yeah, you're seeing the patterns now. Awesome. Because 1 here is not equal to 0, or rather, okay, let me frame it this way, because it's like saying it sometimes is confusing. So the computer asks itself, is 1 equal to 0? No. No means false. So as soon as you see a false on the left-hand side, ignore all this junk. It doesn't matter what came afterwards. So the overall expression is false. Making use again of seeing that false, skipping over that second part. Another useful law that will come up, and while we're talking about logic, is De Morgan's law. You may recall in geometry class, yeah. So this thing is the distributive property of Boolean logic, Boolean algebra. So when you have this expression, the opposite of A and B being some kind of statement, some kind of expression, it's the same as not A or not B. Right? So as you distribute these things, think about like, oh, what's the opposite of A? Not A. What's the opposite of B? Not B. What's the opposite of and? It's or. So these expressions are the same. And then going the other way, right? If you have an or expression and a not outside, you can flip all 3 parts and get this thing. I'm getting tired of reading them out loud. Where it's useful, I've seen it really used in like my computer hardware classes when you're down to the ands, ors, and not gates. When you're thinking about, okay, what is this circuitry doing? It tends to less like I haven't seen it come up as much in like bigger software development projects, but it is useful to know. So this might test it out, right? Like on the AP test, if you get like the multiple choice portion, you would see like, oh, like which expression is equivalent to blank. And you can save yourself some time knowing De Morgan's law versus like evaluating and checking each expression to see if they output like true or false. So we see the distribution of the ands. Notice these 2 symbols, greater than and greater than and less than or equal to, those are opposites. Same with these 2 symbols, equal to and not equal to. And then notice in the middle, these symbols are flipped. And on your own, you can go through and check it to see that overall, this whole expression and this one give you the same thing. We'll skip over this first example because we didn't really talk about the values of char. Right? So it's true because B right here, if you think about all the characters or all the letters, they're lined up in an order. They're mapped to some kind of number, right? So B comes after A. So then this one ends up being true. B is less than F, right? Because B comes before F. So that's why this expression is true. We'll go over those another time, but that's not expected of you now to understand how char works. So the second one, though, is something you can walk yourself through. All right, int nh, 16. What would be evaluated in this expression? Very good. Yes, very good on the student that said not true. Often when I'm working through these problems, right, like the one thing that I think is common, right, when we focus in on like substituting, okay, this is 16, this is 16, this one is gonna be true, and we see that 16, okay, it's true and true. So then I stop here, right, and then I box my answer. I say true. Well, oh shoot, wait. Hold on, Mr. Chan, you forgot about the very important not. So I appreciate the student that said, like, this is the answer, not true, which is false. All right, notice I misused the equal sign there. It's the math implementation of equals, right? It's the assignment operator in programming, so that's like totally different, I bet. All right, nice. Clicky click. Cool, how about this one? Yeah. It's going to be false. You're seeing De Morgan's law in play, or you could evaluate things and check your work that way. So I find the bottom one to be easier to like check, and this one a little bit more complicated. So you could like, with more practice, go between these two. All right. So here's the third idea. We talked about Booleans. We built on those with logical and relational operators. And the last one is, okay, why are they useful? We need them in order to implement a flow to our code, implement complicated logic. So how does computer implement that? It checks things with if statements. So notice this inside parentheses, right? Notice the syntax here, if, and then some expression, some squiggly braces or curly braces, and then a block of code. Right now there's just one line of code in here, but you can imagine you can have a bunch of different lines of code inside. And this structure is called an if statement. So it checks to see, okay, is this expression true? If it is, it executes this line of code. Otherwise, it skips over whatever's inside these squiggly braces. Together with these, so you're noticing some more syntax. This is called an if-else statement or an if-else block, right? If whatever x is true, it executes this code. Else is the catch-all. So if this first one, if this first if statement is ends up being false, it skips over this and then it goes immediately to the else. Right? From your prior programming experience, hopefully these look familiar. If not, then you'll need to like read up on Unit 3, and it walks you through a lot of these ideas. So the most complicated one is the if-else if statement. So that's this middle section here, right? And since it's the first time we're seeing it in this class, maybe I'll annotate and walk you through a couple of these examples. Let's say temp, right, has a value of 75. Here's what the computer is going to do. It's going to check. First off, is 75 greater than 80? Nope. So it skips over this line of code. It goes down here to the else if. It checks, is 75 bigger than 65? Yep. So then it runs this line of code. And then it ignores this line and ignores this line. And if there was something else down here, right, tried to draw a smiley face, then it would execute that line of code. But treat this if-else and the else-ifs as one whole unit, right? Hope that's helpful. So pause if you want to take a picture of it. Think about what values would get you down here to get this line running. As we're waiting, anyone need the picture? Okay, I'll take that as a no, so I'm going to erase some of these. So then if you wanted this third statement to run, what would be the value of temp right here to get it to be cool? Yeah, that would work. That's one answer. 55 would in fact run cool, because 55 is not bigger than 80, it's not bigger than 65. Yeah, 51, yep, and then Justin's got it. You want anything that's strictly between 65 and 50. And then just to see that you're understanding else statements, name a value of temp that would cause it to execute its else block. This have the word cold printed. Good. Right. So it's kind of working backwards with if statements, flexing our brains to see that we understand what's going on. Nice. Cool. So a student messaged me about lightning. So if you're getting ahead in the class, like you'll have to wait a little bit to get things working, send me an email. I'll reply to it soon. All right, close. So this one's a little weird. It's very common for if statements to have just one line of code associated with them, in which case you could drop off these squiggly braces and only that line of code would be executed. Okay, it's optional, but only for one statement. I think it's best practice just to have these here so that you never run into like an unintentional side effect with like deleting and leaving out these squiggly braces. Do I have an example of that? I kind of wish I had an example. So if you had like, if you had like, what, like system, and then .out .println, and then x here is like, what, smiley face, right, like that, okay? And then you pretend these things weren't here, okay? It's gonna function not as you expected for those beginning programmers, right? It depends on the value of x, but like you expect both these lines of code to run sometimes, both of them not. And I think it's just easier to leave these squiggly braces in, okay? And then surround the lines of code you want to run with this if statement. But it's handy to know that if a programmer does write an if statement with only one line of code, then that's what they mean. Okay, so going on with if statements and short circuiting, yeah? So in math, we can't divide by 0. And in computer coding, that's the same idea. It throws an error, okay? So notice in this line, when it first tries to check this, right, is 1 divided by 0 is not equal to 0, well, it gives you an error right here. But notice we have that same line of code and we put it after an OR where we're short-circuiting, and suddenly it doesn't throw an error anymore. So this shows you that it's skipping over that when it sees the true for an OR, right, it's short-circuiting happening. It ignores this stuff, so it's not going to throw an error here. It's not going to break your program. Okay, but if you do the opposite, right, even though you're like trying to do short-circuiting, this is where the error is thrown, right here, right? You're trying to divide by 0, you know that this part's true, but order matters here. It reads code from left to right. So then this is suddenly not okay, and it throws that same error we got before. I think this is where we'll pause. Thursday, we'll talk about comparisons and dot equals. We'll also talk about null pointers and references, because that comes up in Unit 3. There's 2 minutes left to class. You are dismissed formally. I'm going to pause the recording.